Hi guys, in this video we're going to be looking at the systematic approach we take to solving 3x3 systems as opposed to 2x2 systems. And so I'm going to start really with just our goal in terms of solving 3x3 systems and then relate it back to 2x2. So our goal in plain English is really to rewrite the 3x3 system instead as a 2x2 system. And then solving the 2x2 system for its unknowns and working backwards for the value of this remaining third unknown, since we had three variables in the original system. So I suppose the idea is if we had a 2x2 system, guys, we already know how to solve 2x2 systems, so why not rewrite our 3x3 as a 2x2? So let's go ahead and begin by taking a look at this system of three equations and three variables that I have on the left over here. And what I'd like for you to do first is this. We're going to index each of our equations. Now, it's not that switching any of these equations around changes the value of the solution to the system. So that XYZ order triple that plugs into all three of these and maybe works, it's not going to change if you switch your first and third equation around. So I want you to know that these numbers here are just kind of placeholders, but it's really going to help us kind of organize our work. So in terms of our first step that we're going to take here, what we're going to do is we're going to choose two sets. So two sets of two equations to eliminate the same variable from. So this looks like it would make sense. It doesn't really sound like it makes sense. Let's take a look at what I actually mean here. And so what I want you to notice is we're going to choose two sets of two equations. So that is to say, I'm either going to choose equations 1 and 2, 2 and 3, or 1 and 3, but our goal is going to be to either eliminate the x's, eliminate the y's, or eliminate the z's. And just kind of scanning this problem here, I think it would be really easy to work with our x's just because the size of their coefficients are all the same. Just they may not be opposites yet, but we can modify that with multiplication there. So what I'm going to choose to do is I'm going to choose my first, let's write this down, first set of two equations. And in this case, I'm just going to go ahead, because it's convenient, I'm going to choose equation 1, I'm going to choose equation 2. And of course, what we tend to do is always just rewrite what your equations are. Sorry, let me pop out of this here really quickly here. Z, go up here, 100. That's a little bit easier to see. So we're going to rewrite equation 1. So equation 1 has this 3x minus y plus z equals -1. And our equation 2 is 3x plus 2y's, okay, minus 5z's equal to -16 here. So since we're going to eliminate our x's, it would be prudent for us to make sure that their coefficients are opposites. And so in order to do this, I'm just going to go ahead and multiply the first equation times a -1. Remembering that I have to multiply everything in this equation by a -1. What this is going to do is give us this same set of equations, but a little bit modified, where our first equation now, since we multiplied by a -1, everybody has become its opposite value. Our second equation, which we didn't scale at all, becomes this again. And what we're going to do is we're just going to add these together. That idea here was to eliminate our x terms. What you notice is we get left with a new equation that has just y and z. So specifically, y plus 2y is 3y, z minus 5z, negative z minus 5z is -6z, and a positive 1 with our -16 here is going to give us a -15. So I'm going to box this, and we're going to give this a name. This is our first modified equation. Okay, groovy. Now what I want to do is, again, choose two equations to eliminate the same variable from, but I can't choose the same two. So that means I have to choose either equation 1 with equation 3 to eliminate my x's with, or I have to choose equation 2 with equation 3. In either instance, it's going to be two new variables that we're still eliminating x from. So what I'm going to do is I'm going to write second set of two equations. I'm trying to stay as organized as possible here. And this time, why don't I go with equations 2 and 3, just because it's arbitrary in this case. We have 3x plus 2y minus 5z's equals -16. In this bottom equation, we have 3x plus 3y's, okay, plus 2z's, and this is equal to 6 here. We want to eliminate our x's again. So again, in this case, it's effective to multiply by -1 on either of these equations. I'm going to do it in this, what happens to be our second equation of the system. But let's go ahead and rewrite our two equations here so that it's modified. -3x minus 2y plus 5z equals a positive 16. And our third equation here, which was the second equation up here, okay, stays the same. So again, we see our x is eliminating, and this is the profound thing about this. We get left with the new equation, 1y plus 7z's equal to 22 is our constant. I'm going to box this. We're going to give it a name as our second modified equation. And the thing that I really want you to see here is this. We now have two equations that have the same y and z value as the original system does. And both of these equations that are left over both have just y and z, not y and x on one of them and x and z on the other one, both y and z. The intent was to get down to a 2x2 system. So now that we have these two equations that their y's and z's mean the same thing as the y's and z's in the original, what we're going to do is we're going to write a 2x2 system using our new modified equations. Okay, modified equations. And then we're going to solve for the unknowns. Now at this point we can set up our 2x2 system. I'm going to do that here. So I'm going to write 2x2 system. I would recommend that you do the same thing if it's necessary here. And what we're going to do is we're going to put in these two red equations. So let me go ahead and keep them color consistent here. Red equation number 1 was this. And our other modified equation number 2. Okay. Oh, that 15 looks bad. Let me fix it. There we go. We had 1y plus 7z's, and this is equal to 22. Now the fact is, if I had a system like this to begin with, that'd be a whole lot easier to work with because, well, it's just less variables, less equations. We could use either elimination, substitution, or a graphing method here. I'm going to push you, in this case, towards using elimination just because that seems to be what we use a lot with larger systems. But if I'm going to eliminate here, I have to choose which variable I want to eliminate. Do I want to cancel out my y's or cancel out my z's? I notice that my z's here are already opposite signs, but 6 and 7, the very first multiple they have in common, I think, is 42. So I don't want to scale both of my equations up so big that I get big numbers. Let's try to eliminate our y's here. It would just be much more simple or simpler to multiply our second equation by a -3 in an effort to get this y down here to have a -3 as opposed to the +3 up here. So we're going to rewrite our system. Again, we have 3y minus 6z equals -15. And down here we have -3y plus 7z's. So, no. Sorry, we're scaling this. So -3y, -3 times +7 is -21, Mr. Allen. All right, -3 times a +22 is -66. Okay, so when we work with this here, again, we're solving this using an elimination method. I notice that I have -27z's left over here. And just to be clear what we get here, let's get out a calculator. We don't want to make any mistakes. So let's see. Last time I checked, a -15 plus a -66 gives us a -81. Now, what would I do at this point? Well, hey, you notice that now we've eliminated y. We have one equation with one variable left. We have to be able to solve this for the unknown. And in this case, it's just effective to divide both sides by a -27. So let's ask our calculator here, just to be sure. If I divide by a -27, how many times does that fit into 81, -81? It's 3. So what we're going to do here is we're going to say z is 3, and oh my goodness, you're going to box this. We're going to find a spot to write our solution. And the very first thing I want to indicate is, in our ordered triple, dudes, we know that the z part is 3. So how can we find the value of the remaining unknowns? Well, remember, when you solve a 2x2 system, once you find the first unknown, we kind of just go plug it back into either the first equation or the second equation to find the other unknown, which in this case, we're looking for y. So if I'm going to plug this z value of 3 back into either of these equations here, and it doesn't matter, I'm probably going to choose this one right here because y already has a coefficient of 1. So let me show my work down here. I'm going to have y plus 7z equals 22. That's our equation here. And what I'm going to do is I'm going to go substitute in this value of z that we know it has a value of. So 7 times 3 is 21, right? And if y, which is some number plus 21 equals 22, what that would imply, or we could deduce, is y is equal to 1. So again, I'm going to box this, and immediately I'm going to run over to my solution and say, hey guys, by the way, I know that y is 1. So the question we have to ask at this point is this: how do we solve for the remaining unknown? And that's what we're going to put on this third step here, is use the two known variables to substitute, to sub back into any of the original 3 equations. Original 3 EQs. And what we're going to do is we're going to solve for the remaining, thanks for being patient, unknown. Okay, so make sure you get that written down there. Alright guys, so if we know z is 3 and we know y is 1, which one of our original 3 equations am I going to plug this back into? Well, what are we looking for now? I'm looking for x. And I notice that all of these equations here have a 3 in front of the x. So maybe what I do is I choose an equation that maybe y and z don't have a lot of heavy coefficients in front. So let's do this. Let's take 3x minus y plus z equals -1. We're going to say 3x minus y plus z equals -1. And what we're going to do is we're going to go substitute back in our y value here, which is, let me put it in a different color, 1 plus z, which we discovered was 3, and we get equals -1. Usually what happens, we just combine like terms here. So -1 plus 3, that's a positive 2, equals -1. And when we solve this last equation, we get 3x equals, this is a, just to be clear here, -3. Okay, so 3x equals -3. This would imply that dividing by 3x equals -1. I'm going to box this, and I'm also going to go plug this in back over here. So this is kind of the method we use to solve a 3x3 system. It is really a lot longer than solving a 2x2 system, but I think it's worth mentioning that once you find a solution here, sorry about my typing here. Once you find a solution, it is worth your time to go and plug this back into the original 3 equations to make sure that it works. Cheers.